Hello and good morning, students. Welcome to the world of math. How are you today? Wow, that's great that you are fine today. But before anything else, just give me the floor to introduce myself. I am Karel Justin. I am in the age of 21. My year in course is BSA 2, major in mathematics. Actually, I recently live in Tultulan, Tabinas, Zamboanga del Sur. And for this meeting, I am your discussant. And before we go on to our discussion, let's have a pray first. For this Catholic, you may praise the sign of a cross and let put the presents to God. So, Holy Father, guide us for today's discussions. Help us to understand in every discussions clearly and understandable. Help us in every daily life. We all know that we are not here and without your presence. Just guide us, Lord. Give us the fruitful thing that we are going to share for today's discussions. And we all know that we can do this and without your guidance. But Lord, help me and help me. In Jesus' name we pray. Amen. So for this meeting, we're going to talk about my final report, which we can find it in chapter 13, 13.2. And it mainly talks about the certain identities involving Fibonacci numbers. So the main objectives of this lesson is we're going to find out certain identities involving Fibonacci numbers. But before anything else, let's have some deeper information or prior information about Fibonacci numbers, or what is Fibonacci numbers. So when we say Fibonacci numbers, in mathematics, the Fibonacci numbers, commonly denoted f sub n, form a sequence, the Fibonacci sequence, in which each number is the sum of the two preceding ones. For example, 3 plus 2 is equal to 5. So 5 plus 8 is equal to 13, and 13 plus 8 is equal to 21. So that is being talked about. And the sequence commonly starts from 0 and 1. Although some authors omit the initial terms and start the sequence from 1 and 1, or from 1 and 2. Starting from 0 and 1, the next few values in the sequence. Tiling with squares whose side lengths are successive, Fibonacci numbers are 1, 2, 3, 5, 8, 13, and 21. Or 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 5, 89, 144. Or, for example, 1 plus 1 is equal to 2. 2 plus 1 is equal to 3. 3 plus 2 is equal to 5. 5 plus 3 is equal to 8. And 8 plus 5 is equal to 13. 13 plus 8 is equal to 21. 21 plus 13 is equal to 34. 34 plus 55 is equal to 89. So 89 plus 55 is equal to 144, and so on. So the Fibonacci numbers were first described in Indian. So these Fibonacci numbers was mainly described, was mainly happened or was being created in Indian mathematics as early as 200 BC or before Christ, in work by Pingala on enumerating possible patterns of Sanskrit poetry formed from syllables of two lengths. So these Fibonacci numbers can be used also in forming a poetry. And not just for that, they are named after the Italian mathematician Leonardo of Pisa, later known as Fibonacci, who introduced the sequence to Western European mathematics in his 1202 book Liber Abaci. So the one or the author or the person being portrayed in Fibonacci is Leonardo of Pisa, which later known as Fibonacci. Next, Fibonacci numbers are strongly related to the golden ratio. Bennett's formula expresses the nth Fibonacci numbers in terms of an n in the golden ratio and implies that the ratio of two consecutive Fibonacci numbers tends to the golden ratio as n increases. Fibonacci numbers are also closely related to locus numbers, which obey the same recurrence relation and with the Fibonacci numbers form a complementary pair of local sequences. So if we are going to have a deeper knowledge, or if we are going to analyze, these Fibonacci numbers has a lot of similarities to the other formulas or to the other sequences because of its relation and its context. So now, we are going to talk here on how we are going to find a certain identities involving Fibonacci numbers. So first, we are going to identify or discuss is the sum of the first Fibonacci numbers. So here is the pattern of the Fibonacci numbers. So as we can see, or as we are going to stare, it is long enough, but we could conjuncture it. But as we conjuncture it, let's just read the following Fibonacci number. So 0 is equal to 0. 0 plus 1 is equal to 1. 0 plus 1 plus 1 is equal to 2. 0 plus 1 plus 1 plus 2 is equal to 4. 0 plus 1 plus 1 plus 2 plus 3 is equal to 7. Then 0 plus 1 plus 1 plus 2 plus 3 plus 5 is equal to 12. 0 plus 1 plus 1 plus 2 plus 3 plus 5 plus 8 is equal to 20. 0 plus 1 plus 1 plus 2 plus 3 plus 5 plus 8 plus 13 is equal to 33. So this is why by staring at this it is long enough, but we could conjuncture it. So f sub 0 plus e sub 2 plus and so on plus f sub n is equal to e sub n plus 2 minus 1. Okay, so what we are going to do now is we are going to prove the induction on n, or the later situation. We are going to prove, and in induction on n, the base case is equal to if n is equal to 0. So f sub 0 is equal to f sub 2 minus 1 is the main questionable. So since f sub 0 is equal to 0, and f sub 1 is equal to 1, and f sub 2 is equal to 2, we get 0 is equal to 0. Now, in inductive case, let's just assume that f sub n plus 1 minus 1 is true. So as you can see, that in n minus 1 Fibonacci numbers, f sub n plus 1 minus 1 is mainly result on f sub 0 plus so on Fibonacci numbers, fn is equal to fn plus 2 minus 1. So let's just assume if it is true. So is f sub 0 plus f sub n minus 1 is equal to f sub n plus 1 minus 1 is mainly true, or let us just assume that it is true. So what we're going to show, or we want to show, if that f sub n plus 2 minus 1. So as you can see, that f sub 0 plus f sub 1 plus f sub n minus 1 plus f sub n. So if we're going to simplify it, that f sub 1 plus f sub 1 plus f sub n minus 2 plus f sub n is equal to f sub n plus 1 minus 1 plus f sub n. So f sub n plus f sub n plus 1 is equal to f sub n plus 2 minus 1. So it is mainly correct, and we have the inductive case being correct. So next, what we are going to prove, for example, we are going to prove the f sub 1 plus f sub 3 plus f sub 2n minus 1 is equal to f sub 2n for n is equal to 1 or greater than 1. So in inductive case, we are going to assume that true for n is equal to 1. So f sub 1 plus f sub 3 plus f sub 2 multiplied by n minus 1 minus 1 is equal to f sub 2 multiplied by n minus 1. So in base case, n is equal to 1. So the main question is if it is true that f sub 1 is equal to f sub 2. And it mainly yes, because f sub 1 is equal to 1 and f sub 2 is equal to 1 also. So for prior information, f sub 1 is equal to 1 and f sub 2 is equal to 1. In base case, inductive case, we are going to assume for n minus 1. So as you can see, that in f sub 1 plus f sub 3 plus f sub 2n minus 3 is equal to f sub 2n minus 2. So therefore, the result is f sub 2n minus 2 plus f sub 2n minus 1 is equal to 1. So next, solar identity is f sub n 2 to the power 2 plus f sub n a sub to the power of 2 n minus 1 is equal to f sub 2n minus 1. We could check this for many values of n, but proving this is difficult since the term f sub 2n minus 1 will only contain every other Fibonacci number. So the recursion is harder to apply. It is harder to apply, but let's find a formula for f sub 2n. With some luck, we could conjecture. So f sub n plus 1, f sub n plus f sub n multiplied by f sub n minus 1 is equal to f sub 2n. And in base case, if n, we are going to prove. So in base case, if n is equal to 1, so f sub 2 multiplied by f sub 1 plus f sub 2 multiplied by f sub 0 is equal to f sub 2. So therefore, 1 is equal to 1 and it is being true. So in an inactive case, so we are going to assume if it is true that f sub n multiplied by f sub n minus 1 plus f sub n minus 1 multiplied by f sub n minus 2 is equal to f sub n 2 f sub 2 minus n minus 1. So it's equal to f sub 2 n minus 2. Then f sub n plus 1, f sub n multiplied by f sub n plus f sub n multiplied by f sub n minus 1 is equal to f sub n plus f sub n minus 1 multiplied by f sub n plus f sub n minus 1 plus f sub n minus 2 is multiplied by f sub n minus 1. And if we're going to simplify it, the remaining is f sub n to the power of 2 plus f sub n minus 1 to the power of 2 plus f sub 2n minus 2. So now, if f sub 2 plus f sub 2n minus f sub n minus 1 to the power of 2 is equal to f sub 2n minus 1 is the original identity. So we get the original identity. So it's equal to f sub 2n minus 1 plus f sub 2n minus 2 is equal to f sub 2n. On the other hand, if we wanted to prove f sub n to the power of 2 plus f sub n minus 1 to the power of 2 is equal to f sub 2n minus 1, so we get the base, or the base case is if n is equal to 1, so f sub 1 to the power of 2 plus f sub 0 to the power of 2 is equal to f sub 1 to the power of 2, and it is being mainly correct. So in inductive case, let's just assume that if f sub n plus 1 to the power of 2 plus f sub n minus 2 to the power of 2 is equal to f sub 2n minus 3. So if we are going to simplify it, let's just put first the f sub n to the power of 2 plus f sub n minus 2 to the power of 2 is equal to f sub n minus 1 plus f sub n minus 2 is to the power of 2 plus f sub n minus 1 to the power of 2. So the mainly result is f sub 2n minus 3 plus f sub n minus 1 multiplied by f sub n plus f sub n minus 1 multiplied by f sub n minus 2. And if we know, so as we know that f sub n plus 1 multiplied by f sub n plus f sub n plus multiplied by f sub n minus 1 is equal to f sub 2n. Then we get f sub 2n minus 3 plus f sub 2n minus 2 is equal to f sub 2n minus 1. Because negative 3 plus negative 2 is equal to negative 1. So this proof depend on each other in the induction. So this trick is known as simultaneous induction. So that is all for today, for today's discussion, and I hope that you have some lessons, or you understand some lessons that we tackled today.